minutes and then start. We have a very packed program, but perhaps I can start here just by mentioning a couple points. First of all, please post questions in the chat through the presentations, or else raise your hand later on. If there will be a little time, we'll unmute you and let you ask the question, but posting the questions in the chat would be probably the most efficient way. I also want to thank the support, and I'm not sure why it's not showing me. I don't see, I just see a BioRob 2020 NYC on the front. Okay, thank you, Damiano. So let me just continue here. So I want to thank for the general support for our sponsor, Hexel, and the organizing committee. Thanks to their help, we were able to make this attendance to the keynote, workshop, presentation, and sessions completely free of charge. Thanks again, Hexel, for your general support, and sponsor Professor Cecilia Laschi for this talk. Let me tell a little about Professor Laschi. She is a professor at the National University of Singapore, and her research is in the field of soft robotics. And as a young research area, she pioneered this area and contributed to the development of it at an international level. She's a member of the IEEE, of the Engineering, Medicine and Biology Society, MBS, and Robotics and Automation Society, RAS, where she serves as an elected ADCOM member and a co-chair of soft robotics. She founded and served as a general chair for the first IEEE RAS International Conference on Soft Robotics, RoboSoft, that was in Italy in April 2018. So welcome, Professor Laschi, and I'll pass the floor to you. I'd appreciate if you could try to keep your talk under 20 minutes, so we might have 5 minutes for questioning. Thank you.
Okay, thanks a lot for your introduction. I'm now sharing my screen. I hope you can see it fine. So I recently joined the National University of Singapore. Most of the work that I'm showing today comes from my affiliation with the Scuola Superiore Sant'Anna in Italy. So I'm very happy to be here to have the opportunity for this talk at Biomed, because this conference is really in my heart. Let me share a little memory about this. So the very first edition was in Italy. It was 2006, and Paolo Dario was the general chair. I was an assistant professor at that time. I was involved in the organization, and it was really great experience that I always remember very with fun. I wanted to give this title to my presentation, really inspired to that conference, because and the way we organize the program there, because we try to give a definition of biorobotics, and it's actually a balance between bio-inspiration and biomedical applications of robotics. So let me start with bio-inspiration. What's that? We know it's taking inspiration from nature, from living beings, okay, but it's still a bit vague. This inspiration is a very broad word. We know it is a successful approach, and this paper in Nature a few years ago showed how successful it is, because the knowledge, the science in many disciplines grew recently thanks to this interdisciplinary approach that puts biology into other fields, not only engineering, of course. I found some data myself. We see the growth, and it works with robotics as well. And this paper, I mean, analyzed this quite well. It says there is still a lot of potential unexplored, and it also says that we have to team up with biologists to do the right bio-inspiration to be successful with this approach. But why bio-inspiration in robotics? It is usually because we want our robots to do something that living beings do better. But we roboticists, I mean, we tend to forget when we choose our model, our biological model, we take the individual, and we tend to forget that it is the result of evolution. And the goals of natural selection are not exactly the same as the goals of robotics, survival, reproduction. So what we are observing is the result of incremental adaptation. It's not optimal design. And that's why bio-inspiration shouldn't be just copy the biological model. Uh, Usually it's not really feasible, and it's also of little interest, but rather extract the right principles and try to transfer them to our robot design. So I think it's this good implementation of principles that brings to the good science that we have seen growing recently. And the right implementation of the right principles is also what can help us meeting up with biologists, and in turn have a big contribution for even better implementation of principles and even better science. So what's this good implementation of principles? In robotics, it is, in my opinion, this kind of process where we start from the observation of the biological model measurements to extract the bio-inspired principles. And with the robotics tools, so with the robotics technologies, we can build what I call mock-ups, because they are just intended to verify the principles. So they are not robots intended as machines for some application. They are just to verify the principles. But what is the very important steps that we have to take is to transfer these principles and abstract these principles into mathematical models. And then we can build prototypes, robots, to verify the model. So they are not yet the final robots for some applications, but they are our robotics technology is used to verify the mathematical models. And then when the principle has been translated into mathematics, then it can be used for designing robots. And that's our final bio-inspired robot for some application, which is not necessarily in the same shape or same appearance of our biological model. So good science with the use of robotics technologies in this nice loop from the principle to the robot, involving biologists. Our mock-ups verifying, robotic mock-ups verifying the principle can be high interest for them, as well as the prototypes verifying the mathematical models that explain the principles, to come up finally with what we ultimately want, which are good engineering and robots for some applications. And the octopus is really a gold mine of principles for robotics. It was, in my case, my own experience for our group. Actually, its body is incredible for a roboticist because it is completely squeezable. And the arm is also very, very interesting because it's an arm that can elongate and shorten and can bend in all directions at any point of the arm length. So it's an infinite number of degrees of freedom, if you want to tell it in robotics terms. What is even more interesting is that the arm can stiffen, can change the stiffness, and you see, create a sort of articulated arm, in fact, with stiff links. And the principle behind this is the muscular hydrostat, which is a special muscular arrangement. You can find it also in elephant trunks and tongues. And actually, muscles are arranged on different planes in different directions. The octopus, they are longitudinal, transverse, and oblique. And the longitudinal ones can actually shorten the arm. The transverse can elongate the arm by reducing the diameter. The longitudinal can create bendings. And the oblique actually has a role in the torsion of the arm. What is interesting is that co-contractions can stiffen the arm, can tune the stiffness of the arm. We did our own measurements. We discovered that the elongation can reach, on average, 70% of the arm, but we found even more than 90% in some individuals. We measured the force that an arm can apply. And we looked at the tissues inside the arm, the arrangement of muscles and the nerve cord. And we tried to verify some of those principles. This is a mock-up. And here this is a very simple mock-up where we just coupled the longitudinal and transverse action of muscles by embedding cables inside this silicone arm. We tried to keep the same morphology and the same mechanical properties of the material and the same environment. And we'll see in a moment that that's very, very important. We tested some other technologies like the electroactive polymers that are considered to be sort of artificial muscles because with this stacked structure, they can contract. So we tried to use them as sort of contractile units for an artificial muscular hydrostat. And we came up finally with the use of springs of shape memory alloys. So those springs can contract when they are heated. And we arranged them transversely, as you see in the video. But what is important here is this braided structure outside that can distribute the deformation. And you see the springs reduce the diameter and we obtain an elongation as we wanted. And what is important is how we could model the formation of this braid. Then the springs can be arranged also longitudinally, but I'll show you a video of one of the prototypes of arms with SMA transverse springs. In this video, the longitudinal muscles are approximated with cables, and these are the bendings that they produce, while the contraction of the springs at the same time generate an elongation of the arm. This one. Okay, I skip the rest of the video, but we discovered another very important principle in the octopus arm, which is embodied intelligence. This is a quite well-known principle in robotics today. It means that there is a lot of what we consider to be motor control or sensory motor coordination in our robots that actually comes from the interaction with the environment, almost passively. And we found it in this very well known movement of the octopus. It's a reaching movement. You see when a target appears, they launch one of their, they have this sort of bending wave that propagates to the tip. And if we do, we give an acceleration at the base of a very simple arm. It's just a cone in silicon. What we keep here is the morphology, the mechanical properties of the material and the environment. And we see that the water itself creates a sort of bending wave. We went a bit more in depth into the biology, and we found that actually the animal controls this movement with only 3 parameters set by the brain, which means that a lot is done by the arm itself. a lot of the control of this complex movement with many muscles involved. And we also knew from literature that the velocity profile of this bending wave is invariant with respect to the target. And we found it in our robots as well, not only in simulation, but also in our prototype. So we did some experiments to see when it happens and when it doesn't. And what we found is that it happens in water, not in air. It happens when the arm is soft, when the distal part is passive, like in the animal. So again, it's a lot of the control is done by the morphology and the interaction with the environment. So this concept of embodied intelligence and morphological computation is actually at the base, in my opinion, the real rationale for making robots soft, for soft robots, because many tasks can become much easier in robotics if we take it into account. But how can we do that if we consider a traditional scheme for sensory motor control in robotics? In order to implement morphological computation, we need to exploit the mechanical interaction with the environment. So in a sense, we have to add this arrow, which is the mechanical feedback from the environment to the mechanical system of the robot. So we are bypassing completely all the sensory system and controller. So we need to use body compliance and exploit this mechanical feedback. And actually, nature gives us a lot of examples of animals that are soft. We have a lot of soft tissues, even in our body, in bodies where there is a rigid skeleton. And as I said, this is for me the rationale for soft robotics. I like this definition better. It was given by the RoboSoft community. And as you see, the focus is on the large deformations of the body. So soft robotics doesn't mean only that robots are built with soft materials, with low elastic modulus materials, but they can even be built with rigid materials, but with a geometry that allows for large deformations. That's soft robotics. And actually, these bio-inspired principles and the need for modeling them and the need for transferring them into technologies gave a lot of challenges for, let's say, fundamental research on the technologies. And that's why we have a lot of publications of new science and new technologies in this field. This is a paper, it's a couple of years old, and analyzed this very well. I updated the numbers yesterday a bit, but especially what I think it's important is not only the quantity, but the quality of the publications here, because the challenges given by the biological principle are really challenging, and then brought us to develop new technologies, in some cases disruptively new technologies. But now the field is, mature, not so mature, but mature enough for exploring a lot of possible applications for soft robots, and the biomedical field is definitely one of them, because we have this direct contact with patients, like in surgery, rehabilitation, and we consider soft robots more suitable, like in personal care. We tried to review what's existing in the state of the art by trying to look at it from the perspective of designing those robots. So how much they need to be biomimetic. So for example, it's very important that we use robotics technologies, soft robotics technologies in a very biomimetic way when we want to develop artificial organs, or even more with body simulators, but also for prosthesis. And on the other side, how much they need to be compatible with human bodies. So this is the case for implantable devices. In that case, they must be completely compatible, but also for prosthesis, while it's less relevant in assistive devices. I'll just pick a few examples from my own experience. I mean, the experience of our group. We were invited to, already during the research on the octopus, to use the principles and the technologies that we were developing for exploring the development of a soft endoscope. But the idea was not just to have it soft, but like an octopus arm, soft for navigating inside the body, but then able to stiffen to do operations. And that's one of the prototypes developed in this European project. It is a specialty work of Matteo Cianchetti. Here you see that each module has chambers. The actuation is pneumatic here, and there is also a granular jamming technique for tuning the stiffness. We were also invited to build this robot for assisting elderly people. So the idea here is to build a robot that can help an elderly person to have a shower, sort of robotic shower. You see that it is built in modules, and each module has 3 pneumatic actuators giving bending in all directions, and also 3 cables. They also give bending, but especially the combination of the two can help us tune the stiffness of the robot. This is a video from the project. It was a European project with several partners, and the approach was user-oriented, meaning that some experts did pilot studies with elderly people, with their cares. And this is the installation of the arm in a rehabilitation center. And there is also this chair for the patient. So they told us about the external shape and appearance of the robot, and also especially the parts of the body to be reached. Actually, one of them was the lower part of legs, which results quite difficult to reach. I'll skip the rest of the video. A more challenging project was the development of an artificial larynx that was asked by some colleagues at the hospital in Pisa, and we discovered that the larynx is a quite complex organ with many parts with different compliance. So we focused on the vocal cord, and we consider this model with 3 layers of tissues with different compliance. And we did some simulation, then designed our artificial vocal cord with 3 different kinds of materials, silicones. And with this setup, we could put the external layer in vibration with some airflow, and we measured it with a high-speed camera, and actually the frequency of vibration is in the physiological frequency of the human vocal cords. And one of the most recent challenges still brought on by Matteo Cianchetti at Scuola Sant'Anna is European project Ivory Heart that has the objective of building a soft artificial heart with the soft robotics technologies. So let me conclude with a summary. We have seen how bio-inspired principles brought us to a big shift in robotics, from rigid link robots to soft material robots, but especially this gave us a lot of interesting technological challenges for fundamental research in this field, and ultimately this enabled a lot of applications, including the biomedical applications, but many more. I'll finish with just a call. There is a lively community in soft robotics. There is a TC of the IEEE RAS, and there is a conference, as it was mentioned. There are opportunities for student competition. So, I mean, I invite all who are interested to join. And then I thank the many people working on what I showed. These are just few of them, and the several projects. And thank you very much for listening.
Thank you, Cecilia. It's like a virtual applause. And also we are open for questions. So if you want, please write in the chat to ask about some of your questions to Professor Laschi. So if there will be none, I have a question in terms of the materials. How do you see the materials like evolving and combining with soft robotics? Because this seems to be the key aspect of this field.
Yes, it is, definitely so. And what I usually say is that fortunately and unfortunately, silicon is very good. So I say fortunately because, I mean, people like roboticists could easily handle it and build their own robots. And also for students, it's very easy. But unfortunately, because I think we should do, I mean, a lot of further research in this direction, which, I mean, roboticists don't do. But of course, the collaboration with material scientists is very important here. And I see that recently soft robotics is becoming very interesting for material scientists. So I'm very optimistic because they are actually focusing their research onto the possible application with robots. So that's I think, a very important way to go.
So let me go here to the other questions that we are getting from Wensi Shin. He wants to ask whether we should first focus on the applications with different principles or first focus on principles with multiple applications.
It's a tricky question. I mean, when we look at biological models, it's because we have some needs to respond to. But then when you start studying the biological system, you forget your application needs, and you find so many interesting principles to explore, to verify, and you like building robots just to demonstrate them.
So let me go to the next question from Christopher Olofsson. For the shower robot, how does the actually work? Because the robot copying the octopus looks like it needs a center core.
Yeah, this one was not copying the octopus actually, so it was just an arm with a controller. And there were some interfaces that we other partners developed, so I didn't describe them, but then there is a controller making the robot, for example, follow the surface of the back of the patient and so on.
So I'm going to stretch a little and go for the last question, and the questions will be available last in chat. So Nitish Thakur had asked if you can advise how you might incorporate in this biomimetic intelligence in neuroscience ways, like neurotrophic, for example. Are there other examples for CPGs? Can you advise how you might incorporate in this biomimetic soft robots intelligence?
Yeah, that's a very good question. As you know, I also have I used to work in neurorobotics also before, falling in love with soft robots. But so my dream is that the two fields can merge at some time. So I see a lot of, what I see in embodied intelligence, morphological combination is a sort of simplifying principles. So it's a way to simplify the control of complex systems as animals are, in a complex environment. That's a very important principle by nature, to simplify the control. And the same simplifying principles can be found in nervous systems as well. And we know that very well, that also the neural circuitry sometimes is has evolved in a way that it is a complex system, but the control is simplified. You know, I mean, Alain Bertos used the word complexity to indicate some of it, and I see a lot of similarities between complexity and embodied intelligence or morphological computation.
Thank you very much, Cecilia. So again, like a virtual applause, and like there will be questions in the chat. There are at least one more that we won't have time to answer. If you would be terrific. And I'll pass now the word to my colleague, Professor Jiyeon Kang.
Hey, hello everyone. My name is Jiyeon Kang. I am an assistant professor at University of Buffalo, SUNY, and I'm with the Biomed Committee. Before we begin, I will make a brief note to the audience. Please ask any questions for Dr. Amy Bastian in the chat. I will read them at the end of her talk. And I'd like to thank to the generous support from our sponsor, Tyra Motion. The organizing committee was able to make attendance to keynote, workshops, and presentation sessions completely free of charge. Thanks again to the generous support from our sponsor, Tyra Motion, for sponsoring this talk. Now, I'd like to introduce our speaker, Dr. Amy Bastian. It is a great honor for me to introduce her. She is a great neuroscientist and a physical therapist who studies the neural control of human movement. She is the Chief Science Officer of the Kennedy Krieger Institute and the Director of the Motion Analysis Lab. Dr. Bastian holds the rank of Professor of Neuroscience at Johns Hopkins, with a joint appointment in neurology and PMR, physical medicine, and rehabilitation. She studies how people without neurological damage control movement and learn new patterns. Her lab uses computerized movement tracking techniques, non-invasive brain stimulation, novel devices, and robotics to control walking and reaching movements. One major focus of her work has been on the role of the cerebellum in moving, sensing, and learning, and this will be the topic of today's talk as well. Dr. Amy Bastian will give a talk entitled Identify Intact Motor Control in Cerebellar Ataxia. I'll hand over the stage to Dr. Amy Bastian.
Thank you. Thank you so much. It's terrific to be here. Excuse me. Today, what I'm going to do is talk to you about people who have cerebellar ataxia. Before I start, I'll just show you this quick image. This is the cerebellum, which sits in the back of the brain. And this is an example of an individual who has damage to the cerebellum, a degenerative disease called spinocerebellar ataxia type 6. But you can see that there's atrophy or shrinking of this structure with these kinds of diseases. And these are the kinds of diseases that I tend to study. In the past, I've studied these diseases mostly to try to understand what's going wrong with motor control and learning of movement. But today, I'm going to do the opposite, and I'm going to try to tell you what might not be going wrong, which is important for understanding rehabilitation and what we can use for rehabilitation. So I'm going to try to cover whether cerebellar patients can use feedback control effectively as a starting point, and then learn through reinforcement, which is a different kind of learning than we've studied in the past with these patients. I'm going to dive right in and show you what somebody with cerebellar ataxia looks like. This is a gentleman with a degeneration of the cerebellum. And what I want you to notice is that he can still make movement. He's not paralyzed. He has no peripheral sensory loss, but his movements are irregular. They're a little bit disorganized. You can see he makes lots of corrections and oscillations as he tries to touch his chin and then his finger. And his movements are a bit curved, and his trunk is unstable as he's making these movements. So these are all hallmarks of cerebellar ataxia or cerebellar incoordination of movement. Now, one of the leading ideas right now is that the cerebellum is normally contributing a prediction for the nervous system. So as I think everybody in robotics knows, time delay is the worst. You don't want a delayed system. You don't want time delayed feedback. but humans are stuck with it. Everything we feel, see, hear, smell has already happened because there's a delay from it reaching the nervous system. And so this holds true for using feedback for movement control. And so if you don't have prediction, you might have to depend on feedback and you might make errors. So let me show you an example of this. So this is our gentleman moving to touch his chin. He's going to make a correction. And now he's going to try to touch my finger. And his predictions aren't good. And so he's going to get feedback that he's where the yellow dot is when he's actually where the orange dot is. And he'll keep moving because his predictions we think are poor and because he's forced to rely on time delayed feedback. And so for rapid movements, this is incredibly problematic. So the first study I want to tell you about is one that we just published this year. And it's really, we wanted to really understand, are they using feedback control effectively? Can these patients use feedback? And can we take advantage of this? So we have studied people using a robot called a kin arm. The task that we use is very simple. A green dot is placed on a surface that they can't see through. They can't see their arms. They see a white dot that represents their finger. And then the green dot is going to move in either unpredictable or predictable ways. Our unpredictable way is a sum of signs tracking task. And this requires you to use feedback control. It's not very predictable. The feed forward or predictable part of this is a sine wave, which of course, once you see that it is a sine wave, you can actually track it quite well if you have good prediction. And then I'm going to show you how we can manipulate this visual feedback to actually reduce ataxia by giving them a prediction visually that they're no longer able to generate themselves. So this is the outline for this first part of the talk. The first thing I'm going to show you is what the sum of signs stimuli look like and how a control and somebody with ataxia looks when they're trying to track this. So this is a movement of the elbow joint. And so here you have elbow angle as a function of time. And this is a sum of signs ranging between 0.1 and 2.35 hertz. Now, this is what a control looks like. The black line is the target and the red line is the control subject's behavior. So you can see, first of all, it looks like a really hard task, and it is in a sense, but I'm going to show you that people actually do this really well. They can follow the frequency content of it nicely with certain phase lags. Now, if you look at a cerebellar patient, what you see is something like this. This is the same sum of signs stimuli, the black line. The patient is in red. And what you see is, again, a phase lag. The patient is lagging the stimuli. But again, the overall structure of how this movement is taking place is similar. The gain is a little higher. The delays might be a little bit longer, but the patient is actually able to make sense of this and take advantage of the feedback in order to control their movement. So let me show you ways to look at this that are instructive in thinking about how well they're doing at this task. The first analysis I want to show you, it takes advantage of a phasor analysis or a phasor plot. And let me explain what this is. We can plot the behavior of an individual on a polar plot where the gain, that is how much movement they're making relative to the stimuli, is located on the radial axis, and the phase lag is the circumference of the polar plot. So 0 would mean there's no phase lag. 30 degrees would be 30-degree phase lag, and so forth for that sum of signs stimulus. Now, the cool thing about plotting these data this way is that we know certain things about optimality for this. On this plot, I'm showing you a circle that actually represents where the errors would be minimal for this particular behavior. And so when you are moving at a faster speed, let's say if you're lagging 60 degrees behind, because that's the nature of you can't keep up with the stimuli, the optimal thing to do is to actually reduce your gain to 0.5. So you can see right here, the gain is lower. And that minimizes the error. If you were up here at a gain of 1, the error would actually be much greater. Now, if you can track perfectly with no phase lag, you would want your gain to be 1. If you are completely anti-phase with the stimuli, in order to reduce error, you would want to hold still, actually. And so this is a way of understanding where behavior is actually performing, where people are performing well, and how we can look at that. Now, just so you know, anywhere around the polar plot at a gain of 1 just means that they're replicating the signal, but it has different phase lags, and therefore it would have different error profiles. Okay, so now I'm going to show you what patients and controls look like when we look at their data on a phaser plot. Now, this is from the sum of signs stimuli. And what you can see here, low frequency is at 0.1, high frequency is at 0.235, and then we have frequencies that traverse this. The controls at low frequencies do a good job of staying on or in the circle, which means that they're minimizing error. And as they get to high frequencies where they cannot track well, they stay closer to 0. So they have this particular shape or pattern of behavior. Now, our cerebellar patients are spread out a little bit more, but you can see that the pattern of their movement is similar to the controls in that they are able to do the low frequency tracking within the circle, and then as frequency increases, they become out of phase and they reduce their gain. Now, another way to look at feedback control in this particular paradigm is to change the gain of the stimuli and see if the patients and the controls can appropriately modify their behavior for that gain change. And so the way that we did this is we actually we did the sum of signs tracking with the green dot and the white dot, and then we either increase the gain of the movement of the white dot or we decrease the gain of the movement of the white dot and look to see how people would respond, again in the context of the sum of signs movement. And so when we look at this and we look at the feedback gains applied, we applied a 0.65 gain and a 1.35 gain, and controls here are plotted as blue, patients are green, and we look to see how well they were able to approach the right feedback gain. You can see that the cerebellar patients and the controls look very similar. They are both able to change their gain based on visual feedback in the right direction and to the right extent, or close to the right extent. Okay, so far what I've shown you is that cerebellar patients certainly can use feedback, and it looks very much like what controls look like. It's not identical, but it certainly is better than one might expect when you look at a patient and you think about how they move. Now let's think about feed-forward control, or control that requires a prediction of the stimuli and, of course, of your own movement. Here's a control tracking a single sine wave at a pretty low frequency, 0.55 hertz. So there's the stimuli in black and the control in red. And because we have a good predictive model of our body and also are able to make a prediction about the stimuli, they can track this very nicely. Now, if you look at what a cerebellar patient does, well, first of all, you see these big overshoots with corrections, and then they start to adopt a different strategy, but they're never able to stay in phase with the stimuli. They're always phase lagged. So they are unable to predict this very simple, relatively slow sine wave stimuli. Now, if we go really, really slow, they can do better. And I'm going to show you that now on a phaser plot. So this is a phaser plot for this feed-forward control, similar to the one I showed you before. Here's the lowest frequency, 0.1 hertz, and everybody here knows that's really slow. And 2.35 hertz is the highest frequency. We have fewer frequencies in between because we had to deliver these sine waves individually versus the sum of sign stimuli. Controls are able to track with a gain of near 1 with 0 phase lag, and then as the stimuli becomes higher frequency and faster, they drift over to where they should, to 0. Cerebellar patients, though, are approach a general pattern, but you can see that they're not in the circle. They are actually tracking with too high a gain, and they're not able to appropriately minimize this error, suggesting that they're not able to use this prediction in order to be able to perform this tracking movement. Now, these are, of course, these are quantitative comparisons, but I'm showing you a qualitative mapping of that, how that looks in this space. What I want to do next is just simply test the assumption of, well, if we make the movement really, really slow, do we make cerebellar patients look better? And so on the next slide, I'm going to show just that. This is a gentleman with a spinocerebellar ataxia, pure cerebellar signs. And I'm going to first show you him making fast reaching movements. He's going to try to touch my finger and then touch his chin. What you're going to see is that he arcs up, he goes past, and then he has to correct, and he arcs up and goes past and has to correct to varying extent. The other thing you'll see is he knocks himself in the face because he is unable to decelerate appropriately. And his trunk wiggles back and forth as he's making this movement. So if I slow this down, you can see this again. He goes up, over, past, up, over, hits my finger, moves me, past. And this is a very classic cerebellar dysmetria or overshooting. Now I'm going to ask him to move as slowly and carefully as he can. And if he can use feedback control for these very slow movements where the loop time is adequate for control, then he actually can move much better. So let me show you what that looks like. So this gentleman, and that's not even as slow as I had expected him to want to move, but if he moves slow enough, he is able to use visual guidance and feedback control in order to make his movements look better. They're not perfect, but they're pretty good. So the next thing we did based on this was we decided, can we manipulate visual feedback to try to help the patients? This was really based on some work that was done by Nasser Bonpuri in the lab with Alison Okamura when she was back at Hopkins. What I'm showing you here is that a control subject will make a nice rapid elbow movement to a 30-degree target, and it hits the target nicely. Patients tend to be either hypermetric, they overshoot, or hypometric, and they undershoot. And this has been well documented over the years by groups in Europe, Mario Manto, and our group as well. Now, the interesting thing about this is if you wanted to correct a hypermetric patient's movements, maybe you should just shift the feedback, and maybe you should shift the feedback in the opposite direction to make the hypometric patient's movements better. But it's not that simple. So instead, what we see is that these patterns of movements are more complicated than originally thought. So if you look at this graph, this is a graph where I've shown you the starting components of two movements. Which one do you think would be hypermetric and which do you think would be hypometric? Most people would say the blue, or the darker color here, would be the hypermetric. It would overshoot the target because they're going pretty fast, and that the red would be the hypometric because they're going a little bit slow. But what happens is that you get the opposite pattern. And this plays out very robustly across patients, where we think that they're trying to make a prediction here and feedback kicks in, and then they correct online and they make the wrong correction. And it's pretty striking how clear this pattern actually is. This is the early velocity within the movement, and this is whether you over or undershot the target. If you're moving fast initially, you're going to undershoot. And if you're moving slow initially, you're going to overshoot. So we can't just shift feedback. It's more complicated than that. So what we decided to do instead is we added an acceleration dependent gain to the visual feedback. So let me walk you through this. This is an example of a movement made to a 30-degree step target. And the black is what we would hope somebody would do. The dotted line and the purple line are what's shown to the subject and what the subject actually did. So it matches. So this person overshot a little bit and started out a little bit slow. Well, if we take their acceleration profiles, we actually have to invert it and multiply it by a gain. We can show them feedback, which is the green here, that drives them to actually move onto the desired trajectory. And so by showing them they're moving too fast, they actually, or too slow, they actually speed up. And by showing them that they're undershooting the target, they actually overshoot the target less. It's essentially what we're doing here. You can think of it as a phase lead filter. So the cool thing is that we can apply these principles. And again, this is just in a robot, but you can see that people who overshoot, each of these colors is a different individual. People who overshoot need negative acceleration gains in order to be able to be on target. This is with their best gain. And this person is a big undershooter, and you see they need a positive gain to get onto target. And the orange people are pretty good, actually. And so these people didn't need any gain. And so we can reduce things like this overshoot and correction with this kind of feedback. Now, it's not perfect, but it's something that we have never been able to do before. So what we've shown in this first part of the talk is that cerebellar patients can indeed use visual feedback during reaching. We knew they could use it, but they use it pretty well. They can change their movement gain in response to this feedback, and we can even improve simple reaching using time-advanced visual feedback. And so right now we're checking this, and we actually already have this paradigm working well in a 3D arm movement with augmented reality. And the whole goal is to understand if we can do things to improve more natural reaching control, and if we can use that for training. Now, in the last 3 minutes, I'm going to tell you about a second project, but I'm only going to tell you I'm going to show you the high points of this project. This is a project to try to understand if cerebellar patients can use a different form of learning than we usually study, called reinforcement learning, in order to produce a straighter hand path. So again, what I'm going to show you first is from a kin-arm robot, where they were making point-to-point reaching movements in the robot. And we don't let them see their arm, but during the training, we give them reinforcement so they don't see any errors. So they're not using an error-based system to learn, but instead we just give them binary reinforcement. And we don't even tell them necessarily what we're reinforcing them for. So this is what this looks like trial by trial. This is the length of the path that they took to the target, and this is an example trajectory of one of our patients reaching in this two-dimensional space. The black dots here are dots where no feedback was given at all, and the yellow zone is our desired straight path zone, so we want them to move straighter. When we turn on the reinforcement learning feedback, what we do is we take the average of 10 movements, and if they're getting closer on the next movement to the yellow zone, we give them a reward, which is green, which is a you got it signal, and they understand that that means their performance is better. If they move outside of that zone, so they make a curvier reach than they did in the last 10, we give them a negative or an unrewarded trial. They know they did something wrong. And so this patient is exploring, trying to understand what they're supposed to be doing to get rewarded. And you can see kind of all over the place until the very end, and bam, can lock into this new pattern. So this patient could actually get into the target, and late learning, and by the way, the movement speeds are similar, he can make these movements nicely. Now in retention, again, with no feedback, we don't give them any feedback at this point, trying to look at more of the feed forward component. He's definitely in the target a lot more than he was to start with. We've replicated this and published it recently in 3-dimensional reaching using virtual reality. And in this group of cerebellar patients, what we've shown is that if we do baseline trials, this is the path length again, how curvy their path is in 3D. When we start, we can give them visual feedback and no visual feedback. Then we start the reinforcement training. And what you see, it takes a while, but then they eventually begin to make a straighter path. And it was retained without visual feedback and actually retained reasonably well in retention with visual feedback. Now, if you just let the same patients practice, just try to do the best that you can in getting directly to the target, this isn't just a function of reaching a lot. You can see that there's no change here. We're not giving them reinforcement signals. So we think that this is, certainly the reinforcement is important, and possibly the removal of the feedback is important because it pushes them to try to learn some of the feed forward components of the movement. Okay, so I'm going to wrap up. What I've shown you is that cerebellar patients can use visual feedback control in reaching movements, and that we can leverage it to improve their movement, and that they can improve reaching paths through reinforcement learning. You should know DeCow and Amanda, her last name is now Zimmett, I should have corrected that, and Noah Cowan did the work on the first part of this. Noah is my collaborator at Hopkins. Amanda Tyrion and Daniel Wolpert and Matt Staton did the work on the second part, and Alice Nakamura and Nasser Bonpuri did the original work on over and undershooting. So thank you. I'll take any questions anybody has.
Thank you for Dr. Amy Bastian for the inspiring talk. We have lots of questions in the chat and I will read them for the next 2 minutes. A question from Monica. Interesting methodology. Why are you providing visual feedback in this task? Wouldn't it be more interesting to make them rely on proprioception only?
So that's a great question. Thanks for asking. Monica, we originally wanted to manipulate proprioception rather than manipulate vision. So with vibration on the muscles in order to try to improve the reaching movements. But our control of that was not nearly as good as it was with vision. So we started with vision. But obviously you're not going to have somebody wearing some kind of VR or augmented reality goggles their whole life. So eventually that seems like a reasonable target, but we did not approach it that way at first due to having some trouble with the original design. Great question.
Yeah, and the next question from Dr. Neville Hogan. The correct appeared to occur at a regular frequency. What was it? And was it similar across subjects?
Oh, the frequencies, yes, Neville, the frequencies are similar. The frequencies are usually on the range of 2 Hertz. And we think that the correction movements, certainly with visual feedback, are dependent on the visual delay time. And that's why you see them seem consistent when you look at what the patients are doing. There's a nice paper that shows that if you close patients' eyes, this is from Marsden, it's in the 90s, and you close their eyes, you get rid of the terminal oscillation with the cerebellar patients. And so it seems to be due to this feedback, visual feedback loop time.
Okay, just the last question because we are almost at the end of time. From Shukri Liu. I was curious with the reinforced learning paradigm. It looks like participants retain well the learned task, but did we look into how does this learning generalize to similar reaching behaviors?
Yes, thank you. That's a great question. We have started to answer that question. And we studied a new group of cerebellar patients, but we have not been able to complete that because the new patients were more severe and we gave them less training. And so we're going to have to revisit that. So we can't look at generalization if we don't see learning. So some of them learned, some of them didn't, but we had shortened the paradigm and it takes time for them to learn this way. So I think that's a key thing to take away.
Okay, I think the time is up. So I'd like to thank again to Dr. Amy Bastian for her inspiring talk, and thanks to the audience as well. Now we will close the keynote sessions. The questions that we did not have time to answer, we will post them on the Slack. If Dr. Amy Bastian might have a chance, she can post the answers as well. And from now on, the conference will continue with 3 different tracks for our regular sessions. I hope that you enjoy the rest of your time at the conference. Thank you so much. Okay, Jimmy.
Oh, okay.